Okay, this is actually the second of a three-part lesson on energy, work, and power. So basically, before I start, I'd just like to explain something. In these three lessons, there will be no lesson on power. Apologies for that. In fact, these three lessons are only on what is being shared in the content. So let me go through the content again. So in the first lesson, we have already done conservation of energy and efficiency. So in this lesson, we're going to talk about everything that is related to work done. And in the last lesson, we're going to talk about gravitational potential energy and kinetic energy. So power will be discussed in a future video. So the term energy work power is is the name given to the chapter of this chapter. So basically, I will just stick to this name. All right. So let's move on. So the first question you will want to ask yourself is, what is work done? Okay, this is the definition. Work done of a force on an object is the product of the force and the distance moved by the object in the direction of the force. All right. So let's say you have a force F. All right, that is acting on an object here. So what happens is that the force F may push the object and it moves to point B. So if let's say the object moves in the direction of the force to point B by a distance of D, alright, so what you will get is the work done W is equal to force F times the distance D. Alright, so bear in mind the units must be in joules and it's also a scalar quantity. So I'd like you to try these three questions now. After that, you can pause the video at this point in time, and then once you are ready, we may want to discuss these three questions once you're ready. Okay, so are you ready? If you're ready, let's discuss together. So in the first case, if the object remains stationary, is there any distance moved in the direction of the 15 Newton force? Obviously is no. So straight away you know that the distance moved is 0 meter. If the distance moved is 0 meter, let's say work done is equal to F times D will be 15 times 0, which gives you 0 joules. Simple, nothing difficult about this. Alright. So how about the second question? So now you have a second question where the distance moved is 2 meters in the direction of the force. So work done will be equal to the force, which is 10 Newton, multiplied by 2 meters. So you get 20 joules. No issue about this. This is very straightforward. Okay. So how about the third case? So you realize that although the force is applied, a Newton force is applied to the right, the object refused to move to the right. Instead, it moved down 3 meters. So if it moved down 3 meters, it did not progress in any way to the right. So in that case, what is the distance traveled to the right? The distance traveled to the right is also 0 meters. Okay, so you must be careful. What I'm trying to say here is the distance traveled in the direction of the force. There is simply no distance traveled to the right, so it's 0 meters. Okay, so it's 3 meters in this direction, which is down. Okay, so the work done will be equal to 8 times 0, which is 0 joules. Okay, so let's move on to another two questions. So let's try this now. Okay, you may pause the video. Okay, have you finished? Let's go through together. I'm not sure whether you can see this clearly, but there is a path taken here. I hope that you will be able to see. Alright, so if you have not seen this, just draw it. So how do you solve the first question? So again, we go back to the definition. Work done is equal to force times the distance moved in the direction of force. Although the path taken is very crooked, I don't care about the path. I really don't care, because the path might be very, very long, much longer than 8 meters or 10 meters. But the from the beginning to the end, alright, the total distance travel in the direction of the force is only 10 meters, right? Because this 8 meters is not in the direction, only the 10 meters is in the direction. So that means that the work done is simply 15 times 10. So you get 150 joules. Alright, so there's the answer. Now, how about this question? So once again, the path taken is going down like that, but the force in this case is going down. Alright, so although it moves the object moves diagonally down in this direction, alright, I'm not interested in any motion to the right. Instead, I'm interested in the motion down, because the force is going down, the motion down is more important. So the motion down is only 4 meters. So the work done will be 5 times 4. So which gives you a 20 joule work done. Alright, so I hope that you have all the answers correct. If you don't, you can go and redo this question again to make sure that you get it correct. Okay, so let's go to the last of it. Again, you can pause the video first and try it. Okay, have you finished? Now, what do you mean? What happens if you have a situation where there are two forces and they say work done by F? So if let's say they have two forces and they specifically talk about the work done by one of the forces, let's say F here, then you just give the question what it wants. Alright, so you just assume that the W weight is not around. You just consider this force as it is. Alright, so if this force is going to the right and the object moves in this direction down from the beginning to the final position, I'm only interested in the distance moved to the right. I'm not interested in anything else. So in other words, the distance moved to the right to move from this point to this point is only 12 meters. So the work done by F will simply be 12 times 12. So you get 144 joules. So that's the answer. So what's the work done by the weight? So in the same way, you just consider the work done by the weight only. You don't care about the force F. So again, work done, the weight is pointing downwards. So I only am concerned about the direction move downwards. So it's only the 8 meter. This one, 12 meter, is not related to the question. So you have force of 10 multiplied by the distance moved 8. That's why you get 80 joules, right? So that's how you solve for work done. So let's move on. As I mentioned in the content, gravitational potential energy should be in video 3, but I need to touch on gravitational potential energy now, because gravitational potential energy is also a form of work done. Alright, so what is gravitational potential energy? Gravitational potential energy, or GP, which now I would like to use the short form, is the energy stored in an object as a result of its vertical position or height. Alright, so GP is also a form of work done, which I'm going to explain later. Okay, and the formula of GP is mgh. So what is m? M is the mass of the object in kg. G is the gravitational field strength of Earth, which is 10 meter per second square. And H, sorry, it should be small h here. Okay, H is the vertical height of the object above the ground. Alright, so mgh, small h. So let's say we have an object that is falling under its weight. Alright, from this point here to this point here. So let's say the distance that the vertical distance that it falls is h. So the question is, what is the work done by the weight when it falls through this distance? Okay, the work done by the weight is going to be F times D, right? As you know that weight is a force, so it's going to be W times the distance is h. Alright, so F times D becomes W times H, because the vertical height is in the direction of the weight. Alright, but then you know that weight is also equal to mass times gravitational field strength, or W is equal to mg. Alright, correct? Because 5 kg is 50 Newton. So 5 kg is m, 50 Newton is times 5 kg times 10 will give you 50 Newton, which is your weight. Hence, alright, work done, if you substitute this W with mg, is mgh. So that's how we arrive at the formula for GPE. Alright, so actually GP is a form of work done. So because GP is a form of work done, okay, GP is not dependent on the path taken, just like work done, but only on the vertical height. Why? Because the weight always acts vertically down. So if the weight acts vertically down, okay, any work done by the weights is only any work done by the weight must be also in the direction of the weight. So I'm only interested in the vertical direction downwards of the weight. So that's why I'm only interested in the height. So let's say you drop an object from the same height. In the first case, you drop vertically down. In the second case, you drop down a ramp. In the third case, you drop down a curved ramp. Alright, so this first object falls vertically down. Second one goes down through the side of the ramp. And the third case, it goes down through a curved side of the ramp. In all three cases, the work done by the weight is the same. Hence, the GPE is the same. Why? Because the work done by the weight is only W times H. That means W, which is the in direction down, times the direction move in the direction of W. So it's W times H. So because W is also pointing downwards in the second case, and hence the H will still be only the vertical height. Similarly, for the third case, W is pointing vertically down, so the H will still be the vertical height. That's why GP is only height dependent, not path dependent. Alright, but we're going to go to the last part, which is friction. Friction is also a form of work done, but friction is a little bit different. Let me explain. Okay, first of all, in real world situation, friction exists when two surfaces are in contact. Alright, friction always produces heat energy, and heat energy produced can be calculated using work done. Alright, why? Because when friction rub against another body, when two bodies rub against each other, there is actually a opposing force. This opposing force is friction. The frictional force multiplied by the distance moved when you move the two surfaces is actually the work done that produces heat energy. Alright, so in other words, friction which produces heat energy can be calculated using frictional force multiplied by the distance moved. Okay, so one thing to note is that friction is very different in terms of the calculation of the distance. Okay, the work done by friction is dependent on the path taken instead of the specific direction, not like GPE. GPE is dependent on the height, alright, but friction is dependent on the path taken. Why? Alright, I'm going to show you now. Now, this is the top view of a car. That means that you're like on a helicopter looking down on a car. Let's say this car is going on a bend, alright? What happens is that if let's say there is a friction acting against the car, okay, what happens is when you change the direction as you round the bend, okay, you realize that the direction of the friction changes. Alright, let me go back to the first case. In the first case, the friction is going to the left. In the second case, it's slightly pointing upwards. As it goes round the bend, you will realize that the arrow keeps changing to point even higher, right? So because the direction of friction always changes, all right, at every point in time, all right, the work done is the direction of the friction multiplied by the path that it takes for that moment. So that's why, because this path is changing all the way, it becomes the distance moved by friction is 28 meter. That means that the distance d used to calculate the work done by friction is 28 meter, not 20 meter, not 10 meter. All right. So let me consider a case. Okay, this case is easy. Okay, sorry, let's go back to this first. So let me just write down the work done so that it will be clearer. So the work done by friction will be equal to, that means the value of the friction multiplied by 28. So that means that it's not, in this case it's 28 because it is the path taken. It's not the horizontal distance nor the vertical distance, because the friction direction keep changing. Okay, so let's look at one simple example. What's the work done by a constant 3 Newton frictional force used to stop the block from moving? So if the block is moving to the right and it is stopped in 2 meters, of course the work done by friction will be 3 times 2, which gives you 6 joules. Alright, because the distance moved is 2 meters in the direction of friction. Then say, Mr. Loh is wrong. It's actually friction is in the opposite direction of motion. Okay, you realize that actually the 3 Newton frictional force is opposing the motion. So how can it be work done by friction if it's opposing the motion? So in this particular videos, I'm not going to explain this. Probably in the next video, I'll go to explain this in detail. But just bear in mind that the work done is the frictional force multiplied by the distance of the object moved before it stops. Okay, so let's move on. So this is a very complex question. Given that there is a constant frictional force of 100 Newton against a roller coaster from A to B, what's the work done given that the path along A to B is 200 meters? So that means that there's a frictional force of 100 Newton acting on this carriage. So what happens is that along the way, okay, if the carriage is here, you realize that the frictional force is always changing its direction. Okay, as such, okay, the distance traveled will have to be along this path, not the height and not the horizontal distance. So the work done will be simply 100 Newton, which is your force, frictional force, multiplied by 200 meter, because this path is going to be the distance traveled under the constant friction. Alright, so it's going to be 20,000 joules. So I hope that this few questions on friction and work done has clarified your doubts. Alright, so let's just summarize everything. So work done is force times distance moved in the direction of force. No work is done if the motion is not in the direction of motion. Example, perpendicular, or there is no motion at all. That means that if the motion is perpendicular to the force, okay, sorry, there is a mistake here. No work done if the motion is not in the direction of the force. Apologies. Okay. So that means that if it's perpendicular to the force or there is no motion, okay, there will be no work done. So next, GP is work done by weight and is depending on the vertical height. Friction, which produces heat, is also a form of work done, but friction can change direction along the path taken. So work done by friction is along the path taken. Okay, sorry, what I meant here is, so the distance the distance. Okay, to calculate the work done by friction is the path taken. Alright, so that's all for this lesson. I hope that you have a better understanding of the difference between the different work done, and we'll see you in the next lesson. Thank you and have a nice day.